Hello, everyone. Welcome to this very new incarnation of ICTS's Copy with Curiosity. Perhaps many of you have joined us in the past. Those of you in Bangalore, at least, have joined us in the past, the planetarium for the joint event that we used to have for the last 3 years or more, called Copy with Curiosity. Unfortunately, due to the circumstances, this is something that we are unable to have right now. We were supposed to have Professor Siddhartha Gadgil's talk in March, but we had to postpone it. But we decided that curiosity, whether or not there is a lockdown, is always there. And in fact, if anything, people in their lockdown state are even more curious about what is not only happening in the world of COVID, but also in the world of science. And this is why we thought we will have a new incarnation called Kuriosity during quarantine, KDK. This is a temporary avatar that we are going to have on Zoom every month, like the Copy with Curiosity. So please stay in touch. You can sign up for our emails with our outreach team on our webpage. Also, we have these announcements. So you can tune in. We will have a monthly Curiosity during quarantine for the next few months at least. And we have some exciting speakers lined up. Siddhartha Gadgil is a very well-known mathematician, and I'm very happy that he agreed to participate in this experiment of doing it live on Zoom. Before I hand it over to Professor Amit Apte of ICTS, who will introduce the speaker, let me just say a few words about ICTS itself for those of you who have not been to our campus or are not here for the first time. ICTS is a center of the Tata Institute of Fundamental Research, TIFR, in Bangalore. It's one of the newest centers. It is, we are located in the outskirts of Bangalore in Hesarghatta, and one of our main mandates is outreach, science communication, and we have had a very active program in that direction, which includes a lot of public lectures and other general interest seminars, which are broadcast live on YouTube, and of course the Copy with Curiosity series. So we plan to restart many of these activities in online avatar, but please look at our webpage for both these activities as well as many scientific activities which at ICTS will also continue in an online format, and some of them will be opened out to members of the public. So again, I urge you to keep an eye on our webpage for exciting events that are planned. So let me now hand it over to Amit, and he will introduce the speaker. Over to you,
Amit. Okay, thanks, Rajesh. Yeah, so I'm not in the International Space Station like Rajesh was, it seems. I'm at my home. Hopefully it will not be too noisy. I tried to find a quiet corner. Just before I start introducing Siddharth, I would like to make a few, housekeeping announcements. There is a question and answer chat, well, not quite chat box, but a question and answer box, which you can click on if you want to ask questions. I would suggest that it would be nice if some pressing questions are asked during the talk, and if there are questions that require a longer discussion, can be held until the end of the talk. That will just make it easier logistically to handle questions. But the speaker suggested that he will actually pause in the middle also, and just to catch up and see if people have questions or not. So we will do that. For those who are watching on YouTube, there should be a chat window on the side of the live YouTube. And if you ask question there, we will also try to answer as many of those as possible. We will see if we get to answer all of them or not. But yeah, so those were just few logistical arrangements. I guess I would also like to add that we of course used to conduct these talks in the planetarium, Jawaharlal Nehru Planetarium in Bangalore. So their support has been extremely valuable until now, and it continues to be very valuable. So if you haven't been to the planetarium, please do so. They have lots of activity. They have, yeah, I guess they used to have lots of activities currently, which is on a bit of a pause, but they will start as soon as possible, surely. So their collaboration will continue as soon as we come out of this lockdown and have actual physical talks. And the third part about this talk was this was originally planned in March on the occasion of the International Day of Mathematics, which has been now announced as a by UNESCO as a sort of international activity. Several international activities were planned. Some of them actually did happen, even with or without lockdowns. So some of the online activities also happened. We didn't quite get to doing this talk online in March itself. It took us some time to figure out exactly how to do these things. So we are really glad that Siddharth agreed for this postponed talk. And I guess every day is a day of mathematics. So it's perfectly okay to have the talk today. Okay, so after these announcements, it's a pleasure to introduce Siddhartha Gadgil, who is a professor of mathematics at IISc in Bangalore. In fact, he's a native of Bangalore and IISc. So he did his bachelor's at ISI Kolkata, from where he went to do a PhD at Caltech. And then after spending some years as a postdoc at Stony Brook University in the US, he came back to India, first at ISI and then at IISc, where he has been for last several years, about a decade and a half or so roughly. His activities, his main research activities are in topology, low dimensional topology, related areas like geometry and so on. And but as he says on his webpage, his main focus, or one of the main focus, I guess, is automated theorem proving, trying to get computers to do mathematics. So I guess we will hear a lot about that today as to exactly what that means. What do you mean by getting computers to do maths? So apart from the professional and mathematical activities, he's an excellent teacher, as I've heard from many of his students in IISc firsthand. While talking to them, it comes in obviously the fact that he is a great teacher and he inspires people to do mathematics and love mathematics. He also has an interest in exposing mathematics to people. If you go to his webpage, you will see several expositions in terms of demos, online demos, or articles for general scientific audience. And so hopefully this talk will be one of those great expository talks that I'm looking forward to. So Siddharth, over to you.
Okay, thank you very much for the kind introduction and for the opportunity to speak like this. And thanks all of you for coming. Yeah, it's a great pleasure. I have been to ICTS. Actually, I used to cycle near there even when the building was under construction. So I think I've been there before anyone who's currently at ICTS. Okay, so I'll just, yeah. I'm sorry. Yeah, so I'm sharing my screen. Sorry, I'm just turned off my video, so it's not a problem if you're not getting it because my internet is a little bit erratic. So I turned it off and I have shared a screen. If there's any issue with shared screen, please let us know before I think I should start now.
Yeah, you're good to go.
I see two raised hands. Is the thing technically fine? Should I go ahead?
No, it looks fine to me.
Okay.
Yeah.
Then I'll just start. Okay, again, thank you, ICTS and Planetarium, even though I'm not lecturing in the planetarium, and all of you for coming, of course, are coming in the virtual sense. So I'm going to talk about automating mathematics, but the most important part of my title is that question mark there. Okay, we have not succeeded in automating mathematics. I mean, collectively, personally, very, very far from it, but even collectively, mankind has not succeeded. So but there's a lot you learn from trying to do things, and one hopes this will happen in the future. So as I said, while I'm talking about this, my webpage I have just put up on this slide, and all my activity related to this is in the GitHub repository, which I will just show you here on the screen. You can go there later. The website is here. By the way, these slides are also online. They're already online. Later, I'll share a link to them. Not here. They're there. And so to begin my lecture, so here is the setting, if you wish, of the lecture. So in the goal of automating intelligence, what was considered maybe a landmark year was 1997. This was the second match between Kasparov and Deep Blue, and Deep Blue defeated Kasparov. So chess was considered one of the pinnacles of human intelligence, and this was a case of computer beating humans at it. But in a sense, it was a false landmark. It was a false landmark because you can think of an analogy like saying that propeller planes became faster than diving falcons. So the fastest flying machine was faster than the fastest creature in nature, but a propeller plane has still not broken the sound barrier, for example. So you can tweak and push and you can go only that far. So there was some fundamental sense in which a Deep Blue-like machine could only go so far. And in particular, where it certainly could not reach was the East Asian game, played a lot in China, Japan, Korea, called Go. At that time, for example, my fellow grad student, Hao Li, who's a very successful mathematician today, he was a highly rated amateur Go player, and he said he can comfortably beat the best computer, giving it a large handicap as well. So Go we'll come to these in detail. But the point is that even though this seemed like a landmark, people immediately pointed out that there was some fundamental limitation. And Go was taken as a much more truer challenge. And in fact, as recently as 2010, most people would predict that it will take another 100 years before computers beat humans. But in 2017, a system called AlphaGo defeated SEDOL, who was a 20-time world champion in Go. This is a landmark. We'll talk a lot about it. You notice one difference, though, which we are all familiar with. Deep Blue was one actual physical machine. The system that beat AlphaGo is not a physical machine. It is something that sits on the cloud. Yeah, so it's it's really a piece of software running on a cluster. And of course, this is, all Indians would recognize Ramanujam. Since this was a talk in India, I chose the most recognizable face for mathematics. Well, do we have a computer like Ramanujam? Not yet, clearly. And this talk is going to be really about questions about this. So whether this will ever happen, when, if it's going to, but by far the most important is how, because when we are talking about technology, it's not that you sit by and watch it happening or question whether it happens or not. You make it happen. You meaning collectively, all of us make it happen. And so really you want to think about what it will take to make it happen. That is the most important. Of course, these are all intertwined. And so since it hasn't happened, I can't talk about how it will happen. Instead, I'll talk more generally about reasoning and other tasks like AlphaGo, AlphaZero, and also other kind of computer mathematics, not yet good enough to be a Ramanujam or even a typical working mathematician or even a very good mathematics student, but still various different things on, let's say, different sides of the main issue to try to give an indication of what the road is ahead. Okay, so just roughly to give a sense of the talk, I'll start by just explaining what mathematics is and mathematical proofs, since it's not assumed that the audience here really knows what research mathematics is. I think a fraction of you will not know, maybe majority would not know. Then I'll talk about some generalities about reasoning, and then I'll turn to talking about artificial intelligence, especially with games and other things. And then I'll come back to mathematical proofs and mathematics, both computer and human mathematics, to give some sense what is possible or not. Okay, so this is a talk which is really an exploration. It's a adventure, not the talk itself. It's the quest. It's a talk about a quest. Yeah, so let me just start with what is mathematics, in case you don't know. Here I mean mathematics in the sense of what you call research mathematics. And I'll take as my example number theory, though this is a field I don't know because it's easy to state. And really all I assume is you know what are prime numbers. A prime number is a number with exactly two factors, 1 and the number itself, like 3 and 5, but not 4, which has 2 also as a factor. So 3, 5, and 7 are primes, but 4 is not a prime as it has factors 2. Now these are basic object of study in mathematics. Now why would you bother to study primes? I'll come to that later, not at length, but I want to keep things clear. I don't want to mix up two things. So I'll say what we study first, and then give some indications of why we would study it. Okay. So first of all, let's look at this. These are small scale data that I did on the same laptop actually. This is not large scale experimentation. Let's look at primes. You see there are lots of them in the first row, and as you go further and further, they start getting rarer. This row between 73 to 89 has just 4 of them. Now let's jump here. They're getting rarer, but they seem to be there some amount. There are 2 in a row between 400, down these 400s, and well, down to 1 in a row between 900 and 1000. And I've jumped to 9901. They've become less and less dense. Okay, but we don't know how. I mean, we can't say from this. Okay, so those were the primes. Now we look at something else which is much studied, which are twin primes. So look at 11 and 13 as an example. 11 and 13 are both primes, and they differ by 2. Now 2 consecutive numbers can't be primes except for 2 and 3, because one of them has to be even, and there are no even primes other than 2. But you can have pairs of primes which differ exactly by 2. These are called twin primes. Okay. So for the same data, I will show you the twin primes. Here they are. They've suddenly become a lot rarer. Between 901 and 1000, there are none at all. This is a bit of an aberration. If you look at the same data between 801 and 900, there are a few, and even after this, it's a bit of an aberration. Here, between 9901 and 10,000, there are only 2. I mean, there's 1 pair of twin primes. Now, this is more typical. If you start looking at the numbers of this scale, they've become pretty rare. Yeah, so these are the twin primes. And finally, one more thing I have to talk about before I specify questions. Arithmetic progressions of primes. Okay, so arithmetic progressions is what small children call skip counting. So 5, 7, 9, 11, the difference is always 2. Here the difference is always 3. And here 6. I could even have started with 5 here. But the things we'll consider are things like the third, where you see 11, 17, 23, and 29 are all primes. I could have included 5, but I can't include 35. I have to stop here. I can't continue further because 35 is not a prime. So we'll consider now some relatively elementary mathematics will tell you you can't have an infinite arithmetic progression of primes, but you can have maybe very long ones. So this one has length 4. So we consider prime arithmetic progressions, things like this. And the way we experiment, the last part you can ignore. We are looking at first billion pairs of primes, whatever that means. But for those who know better, let me be precise. What I'm first million arithmetic progressions of prime. What I do is I take pairs of primes and then continue them. So for example, I could have started with 11 and 17 and then continue them as long as we keep getting primes. So if I started with, for example, 11 and 13, then I stop immediately because 15 is not a prime. But if I started with 11 and 17, I go on till 29 and stop. So I take first million pairs and extend it. This is just for the sake of experiments. This is all just informal experimentation. So of length 3, 3, 5, 7, 3, 7, 11, these are a bunch of them. Okay. Of the first million arithmetic progressions, almost 11% or so are of length 3. Okay, so most of them, as you see, about 85% will be like 13 and 15, where you just cannot, 11 and 13, where you just cannot continue it any further. But here there are a million. Length 4, well, there are fewer, there are just 27,000 instead of 110,000 of the million. Okay, so the data is all down there, but I won't show it to save time. So if you look at million pairs of primes and look at the maximal arithmetic progression containing them, 85% of the time you get just length 2. There are about 11% length 3. As you go down these, of length 7, there are only 127. Of length 9, there are 15. Just one of length 10, nothing of length 11. Okay. Now this is small scale experimentation on this laptop, but with good algorithms and good powerful computers, people have found explicit arithmetic progressions of primes of length 27, and this is the current record. Okay, so with these numbers, you can try to guess, are there infinitely many primes? This is one of the classic results of mathematics. It goes back to Euclid long ago, 2000 years ago. Euclid proved there are infinitely many primes. We will actually come to this as an example. So here's the second question. So I said the largest explicitly known one is of length 27. Largest we saw in our data was of length 10, arithmetic progressions of prime. But is there an arithmetic progression of primes of length 1,000,000 or 1,000,000,000 or 1,000,000,000,000? Whatever you want. Are there arbitrarily long arithmetic progressions of primes? Well, this is actually much harder and was answered only in 2004 by Ben Green and Terence Tao. So this is important result in number theory. I'm emphasizing this for a couple of reasons. And about are there infinitely many twin primes? You saw they started getting rarer. Do they end? If there's some biggest twin primes, we still have no idea. Okay. So for two reasons, I've given these list of questions. One is to make clear when I talk about mathematical questions and their answers being proved what I'm talking about. And the second point I want to say is if you say somebody says they're studying mathematics, say number theory, the first reaction is, isn't it all done? I mean, from a common person. So I think the answers to the second and the third say no. I mean, we still don't know this. And in that sense, second is maybe even more important because a field of knowledge can stagnate even if you don't know everything, if you know a certain amount and the rest is impossible. But no, I mean, we don't know everything and we are knowing more and more as the days go by. So it is not stagnant. So this is sort of the first reaction. Of course, the second reaction is, I mean, who cares? Or maybe more politely, what is the use? So this is my sort of section on mathematics itself rather than computer mathematics. So let me conclude by kind of saying why is it one should bother to do mathematics? So firstly, occasionally mathematical results find unexpected applications. In particular, primes and so on are used in cryptography. But this is, I think, a fairly rare event. It's not common. Still, it happens. But far more often, what happens is when you try to understand the questions, like getting the Green-Tau theorem and so on, you uncover or you discover new ways of looking at the world, which are concepts. And these are extremely useful in real life. Okay, so an example I give is one very good one is Gauss, who is a great mathematician. At that time, he was employed as an astronomer and surveyor. So he had to survey land. And when you're surveying large areas of land, you have to deal with the fact that the Earth is curved. But we are used to dealing with curvature as thinking of one object as curved on the other, inside the other. But here you're measuring only along the surface of the land. So even though it is curved in space, we don't have a measurement in space. We have measurement along the line. So you have to understand curvature of land in terms of measurement made on land. This is what we call intrinsic curvature. So Gauss actually did not, while making the measure, discover intrinsic curvature. It took 10 years after that. So it led to the mathematical questions, which were answered 10 years after that. And this was further developed and in particular generalized to higher dimensions by Riemann. So Einstein's general relativity was based on intrinsic curvature. And the fact that Riemann's work was done and Minkowski's and so on was crucial to the discovery of general relativity. Now, a couple of comments. One is, of course, you may say general relativity is not very practical, may or may not be, but many very much more practical things like what is called Berry phase in condensed matter physics also depend on curvature. So this is not just this. And another example is 2016 Nobel Prize in Physics was for topological phases of matter. So this is differential geometry. Topology is a closely related field. So these concepts, when they are used elsewhere, they lead to fairly practical applications and also important science as well. The other comment I want to make here is, so when you're talking about So I'm talking about things discovering in mathematics and then use in application. So point is, well, why not just discover them when you need to apply them? Perhaps the engineers who are trying to build something will discover the mathematics. It can happen, but often it won't, because if you're in a real life situation, even writing software, certainly building something, and you face a conceptual problem, then what you do is hack. I mean, you find a workaround, you find a way to avoid it, because you need your thing up and running. You're not going to spend your time thinking of a mathematical concept which will correctly answer that and 10 years later come and build your device. But if you focus on the right mathematical questions, you're much more likely to actually discover the concept. That said, of course, mathematicians also, we also have our tricks like introducing a hypothesis to bypass the conceptual difficulties. But still, if you focus on good mathematical questions. Okay, so this was simply to introduce people to what is mathematics, why we would do it, nothing to do with computers. The next part also has to do with that, which is just, but getting closer, which is what is a mathematical proof. I said Euclid showed there are infinitely many primes. You see, if you think of the Tau Green statement, I said the largest known sequence has length 27. But somebody can prove that there's a sequence of a length a billion. How can you possibly prove it if you can't describe it? So this is where mathematical proofs comes in. And let me give an example here. Okay, so so this is the theorem of Euclid that I had mentioned earlier, which says that there are infinitely many primes. Infinitude means there are infinitely many primes. Okay, and the way we do it is we do it in several steps. First, we show that every number has a prime factor. Okay, so here's the trick. Let's take the smallest factor of n. Well, n has factor 1, but smallest factor bigger than 1. There is such a factor because n itself is a factor, but n itself may be the smallest factor, something smaller. This must be prime. Why? Because if I take a factor of p, then it also has to be a factor of n, and it's also less than or equal to p. But we chose p to be the smallest factor. So if q is less than or equal to p, then it must be equal to p. Otherwise, it would be a smaller factor of n. Okay, so it follows that the only factors of p are 1 and 2. That is, p is a prime. Okay, this is just an impression if people are not very used to mathematics, but this is a complete proof of these things. That was the first step, to show every number has a prime factor. The second step, which will then give you the result, is given any positive number n, there is a prime number bigger than n. This, by the way, will tell you the main result, because if you had only finitely many primes, take the biggest one, there is no prime bigger than that. So as soon as you know this, so a lemma is a statement you prove for the sake of proving another statement. That is the terminology here. So this is a statement. So the trick here is you look at m as n factorial plus 1. So n factorial is product of 1, 2, 3 to n. And let's take a prime factor of m. Okay. So then p must be greater than n. Okay. Why is that? If p is less than or equal to n, then it divides n factorial. Why? So for example, if p was 3, you see 3 is directly a factor of n factorial here. So if it was some other number here, it would be a factor. So any number up to n is a factor of n factorial. Okay, but it also divides n factorial plus 1, because n factorial plus 1 is m. So if it divides two numbers, it divides the difference. But the difference is 1, and nothing bigger than 1 divides 1. Okay, so no prime number divides 1. So that's absurd. So you cannot have p less than or equal to n. So p must be greater than n. That is, you have showed that there is a prime greater than n, which is this thing. This was to give a flavor of what questions we have and how we answer them in mathematics. Okay. But what we showed just now was an informal proof. It was to convince you that something is true, or the reader that something is true. But a formal proof is something much more rigid. It's a finite sequence of sentences. You start with something which we know, which we call an axiom, something which we take as true about the universe, or assumption, something which we take as true temporarily, or you deduce by rules of inference from what we already know, which could be axioms or assumptions or something we just deduced. Okay. The key thing is this can be checked mechanically. So mechanically, the word literally means by a machine. It could mean by a human sort of closing your brain and checking in a simple-minded way, or it could mean by a machine literally. So formal proof, so informal proof needed a judgment that it's correct. Formal proof can be checked just mechanically. Okay, so here is a formal proof of the same result in a proof system called MIZAR. This is the first touch we are having with computer proving. MIZAR is a system developed in Poland in the 70s, and it has a very large mathematical library, including this proof. Full proof is 44 lines, because you'll notice you'll have statements like by so and so. This is which are previously proved statements, but 44 lines is not so much. And at the bottom, you'll see theorem, this is infinite from unbounded Euclid. Unbounded Euclid is, I think, the lemma that we proved. Yeah. So theorem Euclid is the lemma we proved, and this is the final statement. So this is a proof system that has checked that this proof is completely correct, which is, so this is, yeah. So now I will sort of move away from mathematics. I'll just make some comments about this thing. If you have a formal proof, verifying it is purely mechanical, like the MIZAR proof. However, to find the proof, and this is the key point throughout this talk, in addition to we do computations, we did deductions, but we stated useful lemmas, or we judged that previously known results were true. So I stated the result that every number has a prime factor. So maybe I tried to prove there were infinitely many primes and then decided it will be useful to prove every number has a prime factor. Or in this case, much more likely, I proved that result previously, but when I have to prove there are infinitely many primes, I decided, oh, that will be useful. Now, this is a judgment. There is not a simple rule that tells you that this theorem is useful here, or this is a statement that you should make. You could try to make literally every statement, but that's horribly inefficient. Okay, so you used these things. Also, we considered the smallest factor greater than 1. Okay, if you remember, we showed this was prime, and then I conjectured that it was prime, and then I showed it. So the proving itself is quite easy. Okay, but and also we considered a prime factor of n factorial plus 1. Okay, so this was based on backward reasoning. So I won't explain in detail what this is. This is important. But the thing is, we wanted a number which doesn't divide, prime number which doesn't divide anything between 1 to n. We figured that is good enough. We know that if something divides k plus 1, it cannot divide k. So then let's consider n factorial plus 1. This is the kind of thing which we call backward reasoning. You take what you want to show, go back to what you want to prove. Okay. So now the important point is that you have clear rules for checking a proof. But for finding a proof, we did certain things like introducing results, judging what is useful, and it is much harder to formulate rules for these steps. By the way, backward reasoning, you can formulate rules, and many good proof systems do have backward reasoning as a core factor in their ingredients. Okay, so this is the situation I've tried to illustrate what it is we try to do in mathematics, and how do we are trying to discover results. And we establish those by proofs. These are what we call proofs. Okay, but with this said, we still don't have a formal system that can prove major mathematical results. Okay, so I'm going to go elsewhere into different directions, puzzles, games, and reasoning. So I'll first talk a little bit more generally about reasoning, just trying to put this, what I said previously, in a little bit more of a general context. And at the same time, and then after that, I'll move on to domains where AI actually works before returning to mathematics. But this is perhaps a good time if people have a quick question here. Well, I do see the kind of question that I should answer at the end. Okay, and yeah, so that question will be answered at the end. If there are any other quick questions, we'll. Okay, so I'll go ahead.
That maybe I will just make a quick announcement for those people who joined late. If you have a question, please type it in the Q&A box, and instead of raising the hand in chat or something like that. Chat is much more difficult to monitor than the Q&A box. So if you have quick questions, you can ask it in the Q&A box. And in general, ask questions in Q&A, not in the chat. Thanks.
Yeah. Thanks. I'll resume with this section. Yeah, so, and as I think we discussed in the beginning, so the questions that are about this section, please ask straight away. If there are more general questions, they are very welcome, but right at the end. Okay, when we have seen more anyway, they're better answered at the end. Okay, so I'm going to kind of formulate things in general. So here are puzzles. So here are some puzzles. Well, this jigsaw puzzle is what you saw a picture of. Sudoku, which I don't know how popular it is now, where you fill in numbers so that they add up to 9 in various boxes, rows, and columns. A detective story is also fundamentally a puzzle. I mean, who did something? A quiz question is also a puzzle. And while these are puzzles in the sense of games, I would also say many scientific questions are puzzles, like planetary motions. How do you describe the motion of planets? Not now, but if you were in the 1500s or 1600s, before you knew Kepler's laws of motion, and certainly before Newton's gravity, how do you describe how planets move in the sky day to day would be considered was a major puzzle, which Kepler solved, and then Newton solved at a deeper level, you say. So for me, a puzzle is a precisely stated problem for which it's relatively easy to check that a solution is correct, but it is hard to find the solution. You'll immediately be reminded of my previous slide about proofs. Yeah, so the pleasure of solving a puzzle is because once you see the answer, you know that it is correct, or seeing a clever solution even. Okay, but finding it, there's no clear way. Okay? Now, solutions, of course, may be formal or informal, meaning, for example, with a jigsaw or Sudoku, unless a small child bends a jigsaw piece, if it fits, it fits. Otherwise, it doesn't. That's why you say fit like a jigsaw, almost as a metaphor. And on the other hand, Sudoku, on the other hand, with a quiz question, for example, or a detective story, you have to be convinced that that solution is genuine. Now, solving a puzzle is a mixture of deduction, okay, and intuition. I'll say a little more about intuition. So deduction is algorithms following very specific rules. Like in a jigsaw puzzle, one of the key points is that you look for corner pieces and put them in the corner. You may have to try a few cases, but if you see the picture, you'll figure out what these corner pieces are, and then maybe end pieces attaching to that. Okay, so I solve jigsaws almost completely by rules. That's why I'm really bad at it. But then there's an intuition that a piece is likely to go into some place. I mean, so similarly, so what that intuition is, we'll come to a little bit later. But my general principle I use, this is an illustration from the original Through the Looking Glass, Alice's Adventure there. So Humpty Dumpty is saying, when I use a word, it means just what I choose it to mean, neither more nor less. So when I use words like intuition or puzzle and so on, my point is that the goal of this talk is talking about computers doing mathematics and not what is intuition. So when I use a word, I'll try to use it similar to its common meaning, because that's as an aid of understanding. And I'll try to make precise what I mean by it. But I don't want you to get hung up on whether this is really a puzzle or not. That's not the question I'm addressing. These are words just for convenience. But yeah, so. Okay, so briefly, you have two kinds of reasoning, what you'd call deductive reasoning or algorithmic reasoning, or even algorithmic computation. Okay, so in this case, we perform a small number of steps, and each step is some calculation or move or deduction, and they're based on a small number of rules. Those rules may also depend on some parameters if you have a statistical reasoning, but I would still consider it basically deductive reasoning. Maybe you fit the data with some parameters, like with Newton's laws of motion, you can calculate planetary orbits, but you have to calculate the universal constants from experiments. Okay. The point here is that what we consider small and what the computer considers small are very different. That all that prime data I gave carried out something called Eratosthenes sieve, which you learn in 4th or 5th standard, and I can carry out to 100 in maybe a few minutes, and the computer in a fraction of a second carried out to 1,000,000, which gave all those numbers. So the small is a very different small for computers. So that is one of the things that makes computers better, but that's not still good enough. Okay, now, so to solve problems, one thing you can do is just get better algorithms and better deductive reasoning. Now, so one great algorithm is multiplication with carryover. If you think of Roman numbers, trying to multiply them or tally marks, you realize this is one of the great inventions or discoveries in mankind, that you can multiply numbers by carrying over. Similarly, long division. These are marvelous algorithms. They can make a task much, much faster. Fingerprints with detective novels. These were Conan Doyle's and Co.'s actually innovations. And SMT solvers are used for proving. I'm not going to say much what they are for improving, but these are some of the algorithmic reasoning things that have improved greatly. I'll mention these once more. And on the other hand, you have what is called tacit knowledge or intuition. So here I'm going to be impressionistic, close to real world meaning in my view, but it's really just for context. Okay, so tacit knowledge, this is a term, it's the kind of knowledge that is difficult to transfer to another person in some codified way, written down, verbal, telling someone. The best example that I experience is riding a bicycle. You can't teach a child, I mean, you teach a child to ride a bicycle only in a weak sense. You help them learn it. You don't tell them too much. I mean, they finally, you tell them put your leg down the pedal, but that's not the thing that lets them do it. Speaking a language, in fact, even flying a helicopter, lots of activities, especially dealing with the physical world, but lot of cognitive activities also are based on this tacit knowledge. You can't explain it to others. And typically experts have a lot of tacit knowledge, learned through experience. So intuitive thinking, whatever it is based on tacit knowledge, maybe not only on tacit knowledge, but certainly that's a major component. So now the thing with nothing comes free. So intuition has a problem unlike deduction, which it is sometimes wrong. Okay, there is no magic in this. Okay, but it can be very useful. Okay, and to be useful, it has to be correct often enough. So again, when you're talking about your puzzles, I'm taking two extremes. What you call a hunch is something which is sometimes correct, maybe 10-20% of the time. So you have a hunch that this will work, you try it, it fails, then you have another hunch, you try one more thing. Especially when you're trying to do mathematics, you probably try 20 things before something actually works, or 100 things. So hunch is just correct often enough that it becomes very useful, because you can't try everything. And at the other extreme, you would say you judge something as good if it's usually correct, or at least often correct. Again, it can't be infallible. Okay, only deductive reasoning can be watertight, but these, or everything may be somewhere in between. So broadly, we want to talk about reasoning is a combination of deduction, which is follows rules, infallible, and intuition, which has much more powerful at the risk of fallibility. Yeah. So to solve a puzzle, checking a solution should be purely deductive, at least if it's a formal puzzle. However, finding a solution decides what to consider, which here I'm going to use these terms again and again. You see this talk, everything will come again and again, as it should, because it's supposed to inform the first thing. So it's a policy which will you use hunches to decide what to consider and decide how promising the present situation is. Have you made progress, or are you on the wrong track? So here you're using what you would call judgments. Okay? So you could use purely algorithmic rules to decide what to consider. You can also use purely algorithmic rules to judge things. Okay, but if a computer follows this as against a human, the computer has huge advantage. One is that even if your person can in practice consider 10 things where a computer can consider 10 million. Okay, so the quality of your policy can be much poorer. And as far as judgment is concerned, when you make a judgment, you can postpone the judgment to look at the consequences for a while by exploring what happens ahead. And there again, the computer can explore much further ahead. So in chess, sometimes crudely, people are described as brilliant as being able to see 8 moves ahead or whatever else. That's a crude approximation, but of course, computers can see many more moves ahead. So the trade-off is that always, and especially the Kasparov-era systems, depended on that, computers can compensate for the absence of intuition to some extent by these two things. Okay, so now that was all a general context. Now I'll turn to what has actually happened in the world, and which has these things, which is computers and games. By the way, this is from DeepMind's website. It's photo of AlphaGo, which I'll come to in a moment. Sorry, AlphaZero, I'll come to in a moment. Okay, so here's one more general slide. So before I get to what we have in a view. So this actually, the history of computer chess is very old. It goes back to the start of the theory of computation. So there is a paper written right at the beginning by Claude Shannon, who is the father of information theory, on teaching a computer to play chess. And already he formulated things like this. And the first chess playing program was written by Alan Turing, who's the creator of modern computers. Of course, he played it by hand, not with a computer, following the algorithm. Okay. So the rules tell us what moves we can make, the rules of a game, example chess, and what reward we get at any stage. Okay, so when in the case of a game like chess, we win or lose or draw at the end. In the case of say cricket, you are getting a score. So should not think always only in terms of rewards at the end. So sometimes maybe in mathematics you should think better in terms of cricket scores. You are accumulating them. Now, if you want to play a simple game like tic-tac-toe, you simply calculate the reward following up to the end. You don't need anything else. However, in chess, you can't calculate to the end. Even in checkers, you can't calculate to the end as far as I know. Maybe by today you can. But so you need a policy which is telling you what moves to calculate, and a value which tells you in chess terms how likely it is white will win, for example. Okay, so it tells you what future reward we can expect based on present position. These are the two things that you need to play a game. Okay, so already Claude Shannon in the first paper on chess had more or less talked about this, and he talked about simple values and so on. So in chess, for example, a basic value is obtained by counting pieces and pawns with weight. That is, a pawn is worth 1 point, queen is worth 8 points, and bishop and knight, I think, 3 points. A very mediocre chess player like me doesn't go beyond this. We know this much. You read it in the book that they tell you this is the weight, and then you can use that to calculate things. Okay, there's a little more you can do, like double pawns have half a point, and in Shannon's paper that's where he stopped. Okay, and as far as policy is concerned, standard openings also give policy. That is, you play either this opening or that opening. So out of a huge number of policies, possible openings, you reduced it greatly. And the end game where things are simple, there are tables which will tell you just what to play. Okay, so there you have simple policies, but otherwise things are hard. And what is called chess theory and computers expert systems like Deep Blue, they extend these to elaborate values and policies. But these are all human written rules. And people who were developing Deep Blue actually said that one major switch was discovering some, I don't know, semi-covered pawn or something like that in these. Okay, so these are what are called expert systems, where humans try to codify expert knowledge. Okay, so the trade-off between Kasparov and Deep Blue was Kasparov had a much better value and policy functions. So he knew what to consider, and he knew how strong white or black was in a given position, way better than Deep Blue. But Deep Blue could simply consider many more things and also go much deeper. I mean, postpone your judgment to see what will happen for several more moves. And the trade-off meant that by 1997, Deep Blue was slightly better than Kasparov. So I should say that's a bit controversial. So more accurate statement maybe, I'm quoting Kasparov, that between 1996 and 2006 or so, the very best computers and the very best humans were at comparable levels. After 2006, computers have shot far ahead. So that computers, and here I'm still talking about this kind of reasoning. But then you see there was a trade-off, and this trade-off doesn't work for mathematics, and it doesn't even work for Go. I said Chinese game, I don't know how accurate that is. Anyway, East Asian game Go, for sure. There are two problems. One of them is number of legal moves is much larger. So you have 3 times or 4 times as many moves. So trying everything incurs a much larger penalty. We can't look so many moves ahead. Okay. So more importantly, in chess you can count pieces, but the Go, whose board I showed a picture of there, all pieces look like every other piece. It depends on the relative position. So describing a good value function is extremely hard, and even Go experts can't describe why something has a good shape, as they call it. So this makes it very hard for computers, as I said. Yet in 2016, as I said, a Go playing system, AlphaGo, defeated Lee Sedol. At that time, people commented that Lee Sedol, though 20-time world champion, was at that time only number 3 in the world. And if you looked at the games, AlphaGo was still not good enough to beat the number 1, who was KG. But then AlphaGo got better. So this was 4-1. A few months later, AlphaGo played KG, who was the best player in the world, a young Chinese player, and won 5-0. So at that point, this was established. Okay, so what is the difference? So the key point is that the policy and value functions of AlphaGo are deep neural networks that were trained. I'm not going to try to describe what a deep neural network is, because that will take some time, and I have limited time. But the point I want to emphasize is nobody wrote down rules saying what the policy and value functions were. Instead, you looked at a large class of things, whatever they are, and learned. So just like learning to have a bicycle. As I said, tacit knowledge is something you learn. So similarly here, it was something you learn. Okay, so how was the policy network trained? It was trained by trying to predict what will an expert do at a given situation. Okay. So the only analogy I can think of here is that there is, if you watch this movie called Lage Raho Munna Bhai, this gangster tries to say what to do by asking the question, what would Gandhi do in this situation? That was, of course, for a moral judgment, not a cognitive judgment. But principle is the same. You try to see. So there is a large online database of what moves computers make. Expert players made, and the thing tried to imitate the policy network. And then once you have this, you can train the value. You want to know who is going to win, white or black, simply by playing to the end, again and again and again. But you don't stop at that. Once you have a value network, you improve your policy network by trying to play against yourself, and then improve your value network, and so on and on. So this is to start things off, and then you go on here. So by learning, AlphaGo was able to become the best Go player in the world. So now, because these are computers, unlike the brain, it's rather easy to say what happened. So AlphaGo, even though this was hardware from 20 years later, actually considered literally fewer sequences of moves than Deep Blue. Okay, but it had a much better sense of what moves to consider and much better judgment of how strong a position was after that. And also importantly, AlphaGo showed originality. It came up with unexpected moves. There is a famous situation in this game, famous time in this game, where AlphaGo came up with a move which incidentally, by its own calculation, an expert would have played with only probability 1 in 10,000, which this move startled SEDOL so much that he got up and walked away and started pacing up and down for 10-15 minutes before he could compose himself and come back. And many commentators said it's a really beautiful move. Of course, I'm in no position to judge that as far as this is concerned. So at this point, I should say there is a very nice AlphaGo movie, and this is now free to watch. So please go ahead and watch it on YouTube. It is released by DeepMind, the creators of AlphaGo. Okay. So now, when we beyond this, AlphaGo 0 was succeeded by AlphaGo was succeeded by AlphaGo 0, which was even better. And this actually learned to play without any expert games. You started with the rules of Go and nothing else, played against yourself. Initially, you're playing really stupidly, but you see what moves lead to victory and defeat. Just that, nothing else, again and again and again. And eventually, it becomes much better than AlphaGo 0. Someone commented, it suggested that 2000 years of human knowledge was actually a negative value in this case. Start with no human knowledge, you're better than using all of human knowledge. And well, this was generalized to AlphaZero. So the only thing is Go specific features were removed, like symmetry of a Go board. So this could handle various games. In particular, so 3 games it was trained for: Go, chess, and shogi, which is Japanese chess, which is apparently harder than chess. So it took 4 hours of training. This is mildly misleading because this is 4 hours on 5,000 computers running in parallel, 5,000 cores running in parallel. But just 4 hours of training, it became the strongest chess player on the planet. So already the strongest chess player on the planet was a computer, right? So they had beaten these things. Okay, and what happened is that little more play, and it became it discovered a lot of learning theory. It rediscovered, so it was trained for 48 hours. It discovered most standard chess openings. It discarded a few which humans are still playing, saying that these are actually not good, etc. And this, I'm quoting Kasparov, saying that it had a dynamic open style, and it prioritizes activity over material. Okay, so it plays risky games. In particular, it had plenty of queen sacrifices. So the trade-off between Kasparov and AlphaGo is reversed here. Here, compared to human chess players, things like positional advantage, which are really, to a human, very much the intuitive thing, not something you can explain, is what this was even better at humans. Of course, calculations, it was even better. So, okay, so far this was really the goal of this, was to try to emphasize in settings other than mathematics, where AI is, And most importantly, I had wanted to emphasize that it got there because of doing not only what like expert systems computers do well, but what we tend to believe humans do well as well. Okay. So now I'll move briefly to artificial intelligence elsewhere. I'm not trying to say the great achievements. Instead, I'll focus on those that give an example that is relevant to um, mathematics or what I'm going to say later. Okay. By the way, this is a picture of Goa. So here is one. This was an idea that came in 2013. Just a side comment, when I first saw it, they said, oh, this may be useful here and there. And within some years, this kind of thing has become absolutely standard. So these fields are so fast moving. You come up with a new idea with potential and it becomes a standard idea in 3-4 years. I can't think of that happening in most branches of science. Okay. So the problem that was addressed here is that images or games and so on have a natural structure. You have lots of dots, which I can use to compare. But words are either equal or not equal. There is some structure, more or less. So you want to capture some structure of the words associated with their meaning. But what do you do with that? How do you capture it? Well, what you do is you set up a problem. And in this case, you set up a problem that you've given the 4 neighbors of a word, predict the word. Or you could do the opposite, given a word, predict its 4 neighbors. And then you look for solutions that involve having points in space corresponding to the word and predicting from these, predicting the neighbors using these points. Okay, so I've said predicting from neighbors. Yeah, that's what I'm doing, using these points. And this turned out to be rather cute because you get lots of analogies here. Let me just show a picture. This is not data. This is only impressionistic. So what happens is the word Berlin will be maybe this point in the plane. Paris will be this point in the plane. If you take the arrow going from Berlin to Germany and take an arrow of the same length going from Paris in the same direction, you end up very close to France. France will be the closest word to this. This is not data. This is my impressionistic picture trying to illustrate what happens. So what happens is we put all the words in space. And in such a way, we don't do this deliberately. We don't have a notion of capitals or countries. We are simply trying to predict things. And in this process, it automatically discovers this kind of structure. Okay. So coming back to this. So this is an important idea, as I said. When I summarize, I'll come to this. This is more recent, what's called generative query network. So here is another problem. You're given a 3D environment, but this is an artificial one. You look at it from various angles. And then your problem is that you're given another angle from which you have never seen it and say, how does the image look from there? Now, resolving 3D objects is a highly non-trivial thing that our brain does. So this was trying to do similar things. But here a principle was used, which is that we didn't directly find a 2D image from all the points in the, we didn't directly try to solve the problem of describing the 2D image in somewhere else. Okay. So instead, oh, I have a mistake here. I should say 3D image. So instead, you took the 3D image, mapped it to a much smaller number of parameters, a vector in a plane, sort of like the previous one. And from that, you use the prediction for the 2D image. Okay. This may not be very clear, but the key point is just like we had. So there are 2 points I want to make here. One is that it's very important in knowledge, when we understand something very well, it's not just that we can reproduce it. In fact, this is the difference between a student reading a mathematical proof, for example, or anything else intelligently versus literally. So if you read it literally, you know what it says. If you read it intelligently, you compress it and put it in a more efficient way in your mind. So here I wanted to say that you compress the information and put it in a more efficient way, and then use that to answer the questions. And when that happened, color, shape, and size got separated, the way more or less like capitals and cities got separated. So just by solving problems, by trying to do it efficiently, but specifically by having an intermediate stage where you try to do things with less information, you end up capturing meaning very nicely. Okay. So this I'm mentioning because it's a great idea in AI recently. So generative adversarial network. So you have pair of networks competing with each other. So the classic example is one trying to generate fake images and the another trying to distinguish the images generated by the first network from real images. Okay, so this is an idea that you set up a neural network with the task of defeating another neural network and vice versa. This led to enormously better image synthesis. Unfortunately, we know of these deep fakes are quite infamous these days. Yeah, so this is how you get deep fakes. This idea is not directly relevant. Not is this, but it's just this is the last part is something I'm saying in happened as recently as January. Okay, distributional reinforcement learning. So in temporal reinforcement learning, you're trying to predict future rewards. Well, all the time I'm talking about predicting future rewards anyway. But there are situations in the real life, like you're trying to jump over a hurdle, it's a robot. Reward is either very big or very small. So in this case, if you average things, it becomes misleading. You don't learn very well. So an idea that has been around for a few years, I don't know who introduced it, called distributional reinforcement learning. Instead of having one guy predicting, you have different guys predicting. I mean, different guys meaning different networks or whatever they're called. And some networks tend to say if you predict correctly, they become very happy and reinforce their predictions. And or if the prediction is better than what they did, they become very happy. And there are others which react very strongly to negative errors. That is, if you predicted something good will happen and something a little less good happens, then you get very upset. And the next time you give a much lower prediction. So this forms, so naturally you get optimistic networks and pessimistic networks. Interesting thing about this is that in collaboration, so the DeepMind, which I mentioned, creators of AlphaGo, in collaboration with biologists at Harvard, found subsequently in mice dopamine cells, that is in the brain, which are like these positive and negative predictors, different from these. Okay, so we're going to switch gears a bit, move away from AI towards computer proofs in mathematics. I should say this image is from the internet. It should be credited to University of New South Wales. You'll see why this image comes. Okay, so Hilbert's dream, or many people's dream, but formulated by Hilbert, was to have a universal deducer. You write a program or an algorithm. This was before the days of modern computers, which you give it as an input problem, mathematical problem, and spits out an answer, either yes or no, and a proof that the statement is true or false. Okay, but now we know by the results of Church and Gödel and Turing and so on, this is impossible. Okay, now this is practically important. One, because, well, we know we shouldn't keep trying this. I mean, if you could succeed in this, it would be wonderful. But also because you can conclude that there is no single best deducer. There'll be some things good at one thing, some things good at other, because any proof can be found by some deducer, but no single deducer can find all of them. Okay. But nevertheless, there have been some important computer-assisted proofs, though there is nothing which works universally. So the four-color problem is the first very famous instance. This is due to Appel and Huckin, which involved both combinatorial work theory, but also a computer to check many, many cases. A number of cases have come down over time, but it is simple use of computers. A more interesting recent result about 2000 due to Tom Hales was what's called a Kepler conjecture. This was conjectured by Johannes Kepler of the planetary motion. So as you can imagine, it's a very old mathematical problem and was solved relatively recently. And Hales used computers for, again, checking many, many cases. But in each case, it wasn't just a simple check. It was what's called linear programming. Okay. And the third, even more recent example, this is just from 1 or 2 years ago, is a rather interesting one, the Boolean Pythagorean triples problem, but I'll skip the details. You have this was solved by what is called an SMT solver. So I had mentioned those earlier. Okay. So one comment here is all these proofs are extremely long and they're not really human readable. In fact, people will say they're unpleasant. But you should remember, because of the same results of Gödel, Turing, and so on, it is maybe unavoidable. So you'll have lots of simple statements, but whose only proofs are extremely long. So we would like to find a final proof, but we should be aware, a short proof, but we should be aware that such a proof may simply not exist. Okay. Okay, we'll turn to now a more interesting example, something called the Robbins conjecture. So this was a conjectural characterization of Boolean algebras in terms of associativity, commutativity, and Robbins equation. This, I won't go into any details, but this was considered a very important problem in logic, and people like Tarski students, leading people, worked on it. But it was finally solved in 1996, long after it was conjectured, by an automated theorem proving system, EQP. Now, this was just around the same time as Deep Blue bit Kasparov, but one should remember that Deep Blue had the resources of IBM behind it. This was on just university computers. It was nowhere near the same power. And this was not an AI system, it was an older style of search and algorithmic system. Well, unfortunately, to date, this seems to be the only major success of deductive theorem provers. This was remarkable, but seems isolated. But on the other hand, I should emphasize that theorem provers have gotten a lot better, and there are even people, this kind of theorem provers, and there are people combining it with things like deep learning. Okay, and then I will turn to something in which I was involved, which is tangential to the main work that I do. So this is some research that happened in 6 days, exciting days, on the internet, in Terence Tao's blog, starting with a question that Apurva Khare, a colleague of mine, had asked him. And the only thing relevant here is one key step was that when human progress had stalled, I generated a computer-generated but human-readable proof and posted it. You can see it in the form I originally posted here. I posted it saying gross proof time, saying that, look, here's the computer-generated proof. And even though it's gross, maybe someone cleverer than me can make some good use of it. And quite remarkably, well, not remarkable that there's someone cleverer than me, but quite remarkably, someone could understand the proof and extract from it ideas which were then further developed to give the human proof. So the point here I want to make is that while computer-generated proofs are generally considered gross and unreadable, well, this was very much readable, used in results. Okay, so this was generated in an interactive session, but for fun, let's look at a very similar proof being generated by the computer. Okay, this is generated in the laptop. This was just to point out that this was not a supercomputer required to generate this kind of proof. Yeah, so next we look at interactive theorem provers. So these are systems where computer proofs are generated by interaction between humans and machines, by collaborations between human machines. And the computer has two roles here. One of them is to check the proof and also to help you find the proof, because for a human to give a completely detailed proof is really very difficult. Now, some very large mathematical proofs have been verified. The current record is the Fate-Thompson theorem that odd order groups are solvable in the system called COC. Now, very importantly, for proving things in these systems, it depends heavily on the level of automation, how good the system is at finding proofs. Because as I said, supplying all the details yourself is too hard. Okay, so there's an interesting conceptual issue here, which is, well, your computer is supposed to have checked the proof, but what if the proof checker itself is wrong? So this was addressed in the De Bruijn principle by De Bruijn, who made automath in 1968, the first theorem proving system. So the idea was that the proofs are all checked by a small trusted kernel, and this should be in modern times open sourced, well documented and so on. And in turn, people can check that the trusted kernel is correct. So the rest of the system might help you find the proof, but it should finally check it like this. Now, this is sometimes used in practice and sometimes not so well, but a good example of it used is the Lean theorem prover, which has 3 independent type checkers, which are proof checkers, in 3 different languages: C++, Haskell, and Scala. Yes, so now these theorem provers are very powerful. So now mathematics is not really a game, but we can formulate it like a game with rules, and the way we do it are what are called foundations. Now, the standard foundations of mathematics from about a century ago are set theory and first order logic. But formal proofs in these are both very long and opaque. So theorem proving systems, interactive theorem proving systems, which have become very powerful now, they instead use richer foundations. They have evolved over time, starting with the work of Church in the 1930s, and Curry and Howard, and Per Martin Leuf, and various other people. But recently, over the last decade, you have had a dramatic at least conceptual advance. It's not clear practically how useful it is, with the discovery of connections between foundations and topology leading to a field called homotopy-type theory. Yeah, next theme is closely related to the main theme of this lecture, which is what I call formal methods. So we have looked at mathematical proofs, both human and computer, but of mathematical results. So we now turn to mathematical proofs, but not in mathematics. So instead, what we are talking about is describing software, hardware, communication protocols, various things, precisely in mathematical terms. That can often be done. And then we give mathematical proofs to ensure correct behavior. This is what is called formal methods. Now, this gives a much greater certainty of correctness rather than just any kind of test that we will do. But the catch here is that it's much harder to prove something rather than to run a bunch of tests. So there are many software practices, better testing, which can catch errors. Proving is much better than these, but at a big cost. Okay. Now, formal proofs will have to use interactive theorem provers. There's no practical way of doing it without very good interactive theorem provers. Now, as I said, there is a trade-off that proofs are much harder, and they're really worth it where you have to be completely correct always. So an occasional error, like in a website, doesn't matter, and it's not worth it putting in this much effort. So where do you need this? Well, the first case, an example, is the Pentium bug that Intel had, where the chip maker Intel in the late 90s, I think 96 or so, where they had to recall a whole line of processors, or at least offer to recall, because of an error in the floating point operation. It was a silly mistake, but still, so this becomes very expensive. And then you also have to maybe change your foundries where you're casting things and so on. Next year, they had one more of these. So it can be quite expensive because unlike software, you can't patch. The second is the most obvious example. The Therac 25 radiation machine in the 1970s had a problem with its user interface and software. This is radiation for cancer treatment. Unfortunately, a few people died because they got excessive doses of radiation. So safety critical equipment, this is the most obvious reason why you can't afford to make mistakes, because they may kill people. But the third is also extremely important, and a lot of formal methods actually focus on it, even though it is not so obvious, which is, well, many of you may remember the attack on WhatsApp by the company called Pegasus. Okay, so they managed to hack WhatsApp. The thing is, there was a mistake at some obscure corner in the code in the server in WhatsApp. And now it's likely that nobody would have come across this mistake, triggered the conditions that would lead that, even in the age of the universe, leave alone age of WhatsApp. However, when a hacker wants to attack a system, they go looking for such things. So they keep probing, finding, and as soon as they find something causing this kind of error, which is a buffer overflow, they use that to take it over. So systems level software, a bug becomes a vulnerability. Even if in real life you basically never encounter it, malicious people will use that. So that is where, again, you can't afford to make mistakes. And so indeed, here are examples where people have started using formal methods, which is use mathematical proofs assisted by automated theorem proving. Intel has started using them in the design of its chips, so that the chips, as they come out, don't have bugs or have a much smaller chance of having an error, which will then be very costly to recall. And the second example, which is important, is Paris driverless metro. This is safety critical equipment. And indeed, there is a group in Bangalore in Alstom who are also using formal methods with more or less the same thing. Alstom is the same company that makes the Paris driverless metro. So here you're using mathematical proofs. And the Scala compiler, Scala is the language I use, is another example. This is a systems level software. So finally, we come to our conclusion. So we are discussing the future of computer proofs, and the question mark is back. We don't know. You can think of this as a quest or an adventure. We've not yet reached our goal. So before I conclude, I wanted to mention 4 books. Again, remind you of the ALPHAGO movie, which is well worth watching. So the first 2 are about chess. Gary Kasparov's book called Deep Thinking, where he's talking about deep learning and chess, and also his match against Deep Blue. It's very enjoyable. Game Changer is a book about chess from the point of view of what we know after AlphaZero. And the bottom two books, the second machine age and most human, are about issues that I have not touched upon. So I've only talked about capabilities of what we can do, but not the consequences. And the two important consequences, one is economic, and that's what second machine age is about. And the other is about our view of ourselves. Since Homo sapiens, our reasoning is so much a part of our identity. It's a very beautiful book. I would strongly recommend it. Okay, so as I think I have illustrated, artificial intelligence can make moves that we can appreciate later. So what we see as brilliant moves, though we don't come up with them. It can judge value based on future rewards. It can show originality. It can acquire knowledge which to us is tacit. So interestingly, for AI, there's no tacit knowledge since we can always copy from memory of one system to the other. Okay. And it can work with limited or unstructured data by using self-play, playing against itself, and also like in Word2Vec, synthetic tasks you make up only for the sake of learning rather than ones that you actually want to solve. The important point here is, remember, AlphaZero is zero data. Some years ago and even now you might read people saying that AI systems will work only where there is a lot of training data. I mean, this is false, as you can see. So a lot of statements you hear about AI will work only if so and so, just 2-3 years later, they're evidently false. Okay. And very importantly, AI can organize observations naturally and efficiently with capturing global structure. So it can view the world in a structured way, not as just lots of raw facts. Okay. And what about mathematics? Well, foundations give efficient and modular rules for generating mathematics. This is mathematical objects, statements, proofs, etc. Good foundations will let you do this. Modular here means some little part, like a modular kitchen, doesn't depend on the rest of the structure. Okay. And you can also define rewards. This is not so obvious. You need some ideas, but you can define rewards as well, which play the role of winning or losing. We don't directly have winning or losing. You have to decide how much a given proof is worth. Okay. And then there are what are called mathematical heuristics, methods of proofs. So those also can be captured. They can be captured with composite moves, and we can make a good policy, and we can also make a good value. All these need thoughts, they need ideas, one can come up with them, and only time will tell how good our answers are to these things. Okay. And another aspect of doing mathematics for people is that most mathematics we learn is from other mathematical proofs, from watching other people doing things, but also from reading the output of what they have done. So this is really behavior cloning. So you can bypass it in things like AlphaZero, but that needs a much greater amount of computation, and mathematics is too vast. So it's probably not a good idea to even try that. But so fortunately, things like Lean and Coq and so on have huge mathematical libraries, pretty big ones, fast growing, which you can use to learn. In addition, you can try to extract from the human literature using natural language processing, remembering that you don't have to be 100% correct. You may be 80%, 90% correct. That's good enough to learn from, not to follow literally. Okay. So in all this context, I would say that as far as automating mathematics is concerned, appears to me that there are clear approaches. Of course, a lot of work to be done. But what needs to be done, at least what has to be tackled first, there are clear approaches and no evident barriers. Nothing that I can see at the moment is impossible. Okay. So with that, I thank you all for being here, and I'd be happy to take questions.
Yeah. Okay. Thanks, Siddharth. I have not been following the question answer window because I was sharing my screen.
Yeah, I have just.
Yeah. So we will then go on to take questions.
Sure.
Okay. So there are already quite a lot of questions there. So maybe I will read out the question and you can then answer it.
Yeah, sure.
And if you want to say, yeah, so we will see. So the first was how to use automated mathematics for biological discovery.
Yeah, so that is a little bit, say AI is used for biological discovery. So people who are in, say, drug discovery and so on, they tell you So biology is fundamentally an experimental science. Okay, so when you're talking about but nevertheless, so when you're talking about drug discovery as an example, and this could be done even in answering biological questions, for protein folding, people use it. So let me say one thing at a time. So with biological, for drug discoveries, AI systems are good at reducing your million candidates to a few hundred, which you then go and put in a lab. People in materials also do the same thing. They put, they say that, well, sometimes it's AI, sometimes it's just computational chemistry. So what happens is finally your mathematical models are not accurate enough to catch reality precisely, but they are still good enough that you don't have to try huge, you can greatly reduce your candidates. Okay. But as far as automated mathematics is concerned, you see in biology, models are rarely precise enough to be talking about logical proofs. So I would say it will take a long time, if at all. So see, the thing with biology is because of the contingency, historical contingency of evolution, things don't tend to follow very standard laws. So this makes AI powerful, but it makes, so automated theorem proving you can think of as a intersection of artificial intelligence and formal proofs or formal methods. The formal methods part doesn't fit very well in biology because of historical contingency and such things. Biological systems are complex. Yeah.
Yeah. Okay, thanks. So the next one is, I think, shorter. Is backward reasoning used in AI-based systems?
Sorry?
Is backward reasoning used in AI-based systems?
In AI-based systems for what? For automated reasoning?
I guess it's
so no, correct. No, I understand. So yeah. I know. Is backward reasoning used for in AI-based systems? Well, AI-based systems for backward reasoning you will use in mathematical theorem proving systems. Okay, so yeah, in a sense they're all AI-based. So when you talk about AI, they're either expert systems or they're learning systems. So yes, if you're talking about expert systems, which are the dominant form of artificial present proving systems, what I call interactive theorem provers, backward reasoning is a core part of these. It's very important. Now, in what I'm working on as well, it was actually relatively easy to incorporate backward reasoning in a rule-based way to complement what should be deep learning. I don't yet do deep learning. Yes. So backward reasoning can be, if you have good foundations, you can very naturally incorporate backward reasoning in AI systems for mathematics. And yes, they are used. Yeah.
Okay. Yeah. Thanks. So the next one is in the proof of four-color theorem.
Yeah.
Was the role of computer computations limited to creating all exhaustive cases?
Yes. So of all the various things I said, so maybe the Pythagorean triples was the most sophisticated. So the three cases that I mentioned, so in the case of four-color problem, it was really discrete, checking lots and lots of cases. Now, both Kepler conjecture and Pythagorean triples used actually solving equations and inequations. In the case of Kepler conjecture, it was linear programming, and Pythagorean triples, it was what I called SMT solvers. They were all algorithmic. In all cases, a very large role of the computer was just checking lots and lots of cases. However, in the more modern proofs, it wasn't in lots of cases. You also solved inequations, solved and showed they had no solutions or whatever else. There are many other such cases. There's a Smale conjecture, as it is called, which also used compact enumeration, what's called double bubble problem. So there are little bit more sophisticated ways that have been used with still algorithmic sophisticated ways in these computer assisted proofs.
Okay. Yeah, so I will skip a couple of questions because I think they have been mostly answered in the next part of the slides. These were earlier questions. Something about, can policy gradient method RL can do mathematics? I don't know if what value function is information compression measure?
Maybe I'll try to read it. Whose question is this?
This is from YouTube, from Biplab Kavyashri at question from Biplab Das.
Biplab Das. Oh,
yes,
okay.
It's a.
I'm not finding. What time does it say? Sorry.
4:50.
4:50. Oh, somehow it's not in my chat here. Because I lost connection many times.
Oh, you lost connection. If you joined it later, this will not appear. Okay,
Yeah.
maybe we can skip the question if it's.
Can you read it again? Yeah. So okay.
Okay, so can policy gradient method RL?
Yeah.
Can do automatic mathematics?
Yeah. So sorry, I can't answer that. I don't know.
Okay.
I don't quite fully understand the question, and
Okay.
likely the answer is we don't know, because we don't succeed in doing automated mathematics. I don't fully understand, so I can't tell you how potentially useful it is.
I couldn't understand the question fully
Yeah.
either.
Yeah.
Okay. So it's a question from Kevin Buzzard. Where is the training data for mathematics?
That's a very good question. So where is the training data for mathematics?
And then partly the person says Lean's maths library.
Correct. Correct. So as I said, there are more and more formalized mathematics libraries. So that's one thing. Lean Prover has a very large mathematics library. So does Coq. I'm trying to use Lean because Lean also has a very nice export format. So it is able to, it not only has a nice library, but a nice system for sharing the library. So somebody else can use it externally, which I could not find properly documented with Coq. So there is a reasonable amount of formalized mathematics. One. Two, as I said, one can try to use natural language processing and to try to extract from human literature. So far, there is no system that does it adequately. But three most maybe very important to remember that after all, AlphaZero worked with no training data. So what you're trying to do is reinforcement learning by generating mathematics and learning from mathematics as you generate. Okay. Now, AlphaZero demonstrated that that can actually be more powerful than using training data. But of course, will take a lot more computational resources. And also mathematics is very complicated. So you don't want to start off like that. Okay. But still, yeah. So the answer to yours is you already have formal mathematics. Hopefully, we can get something out of human literature. And hopefully, we can train by just self-play. Yeah.
Okay. Question from Rajesh Sundaresan.
Yeah.
Going back to your prime number related theorems.
Yeah.
How do we make a computer automatically recognize that the notion of a prime number is an important one?
So that's
for example, so he gives an example in the Berlin to Germany. How does a computer discover the notion of a capital?
Right. No, so that's actually not immediately. So you can, how do we know that a question, well, how do humans know that the notion of a prime number is important? Well, humans know that, so I don't understand this at a deeper level, and I'm only experimenting with this. So my answer is largely speculative. And in fact, Rajesh probably will understand better than me certain things since they're information theoretic questions. So the thing is, why do humans think prime numbers are important? Well, they're important because there are many non-trivial statements about them. And starting with the fact that every number is a product of a prime. And there are many statements whose statement doesn't involve prime, but the solution involves prime. Okay, so how do you judge that whether it's a concept or a result in mathematics is important? There are a couple of ways, one of which is simply having enough statements that are not obviously true or false. Okay, if this is for a concept. But for a statement, you would say that it's non-trivial if its statement is simple in some appropriate sense, in some information sense, and but the only known proof is complicated in some information sense. One, and secondly, that it has as consequences many other statements. Okay, so you can think of trying to compress your mathematics as efficiently as possible, and those that survive are what you really want, but you can't get to that straight away. But all this can be captured by trying to efficiently generate proofs. Okay, and I think I was saying, so efficiently generate proofs you can measure this by having some sort of an entropy measuring how much work you did in generating the proofs, and use a Kullback-Leibler distance, some kind of distance which tells you how well the statements fit with the proofs. How well this works in practice, I don't know. In baby cases, it works. But in general, when you want to judge, as I said, concept is important. If so, this is of course a natural thing within mathematics we use all the time, right? So you say that something is justified in introducing this concept if you worked on something whose statement didn't involve this, but the solution involved this. Okay, so with primes there are any number of such cases, or they're just interesting statements. Yeah.
Okay. So next, there are a few questions which are a bit unclear. So instead of trying to read it and then we try to decipher the question, I will jump to a question which is slightly clearer. What is the key difference between AlphaZero and Hilbert's computer?
Hilbert's computer. I'm afraid I don't actually know. Oh, you mean in terms?
Yeah, I'm not very sure exactly what the question means, but
yeah. So I'm guessing Hilbert's computer is the imaginary thing that could, given every problem, solve it. Well,
yeah.
Assuming that that is what you mean, this is of course this is of course we know now impossible. So AlphaZero is possible. Hilbert's computer is impossible. Yeah.
Okay. Yeah. Yeah. The next.
Okay, let me answer a question that I see here from
Kevin
MIZAR. Your last slide is optimistic, but have you seen a computer discover for itself a proof there are infinitely many, or even the concept of a prime? Well, I have to just say that Kevin Buzzard is actually more of an expert in this than I am. I don't know. Yes, I am being optimistic. I don't know how realistic this is. I have not yet, clearly. My optimism is only based on what my knowledge of what goes into doing mathematics, and that and other tasks that have been solved using this, plus some concepts that I hope can capture these things. So I don't know. Maybe I'm yeah.
Yeah. So I'm trying to just go through these the question answer window to see which of these. I guess it's also about 5:40. So we have been around for about an hour and a half. So at some point we would probably like to break up. So maybe a couple more questions. Let me try to figure out if I find something that I can decipher in a short amount of time. I don't know how many questions you see, because I don't know when you last dropped.
I see all the later ones. So I see starting with 520, more or less all of them.
Oh,
I would guess.
Okay.
So questions that were asked before the end of the talk, I lost all of them.
Yeah.
So I could see Rajesh's question. Certainly anything after that.
Yeah. Okay. Fine.
Yeah. Maybe I'll answer one question I read here as I say it. Sure. How could deep learning and word embeddings, which are designed to give very good approximate answers, be useful for a task like theorem proving, which requires absolute rigor and precision? Yeah, so it's an important point, but I think, as I said, theorem proving. So I'll tell you a case where they're actually used. There are a few people involved. Joseph Urban is the name I remember, but there are a bunch of others. For example, with first order theorem provers, where this is actually used. This is not word embeddings. This is just deep learning. But yeah, so which would include representation learning. So they are very powerful at deducing things. The problem is that if you start with everything you know of mathematics, you'll quickly hang because the number of consequences are too much. So what you have to do is premise selection. You have to decide what is your starting point from where you go on to proving results. Yeah, so what is your starting point? And this is something which deep learning does very well. You see, so the proof itself is precise, yes. But again, when I was talking about my prime number concepts and various, proof of infinitude of prime and so on, we considered something, we recalled some theorem, this and that. This is a fuzzy concept. What, or even if you think back in your school geometry, in Euclidean geometry, you draw a line somewhere, you draw an arc, you look at where two lines intersect. There are many steps in finding a proof which are not precise. So this was like my puzzle's two sides to it. I mean, what you consider, whether you're correct or not, is a precise thing, but what you consider in trying to find the correct proof is not precise. So deep learning has to be there because you cannot make rules for what to consider. I mean, you can't, I mean, so in practical terms. On the other hand, reasoning proper will be completely algorithmic. So they complement each other. They have to be made to work together. And there are systems which do make things work together. Yeah.
So should we just end with one last question?
Yeah, sure, as you like.
I will choose my favorite, not favorite, but something. Shouldn't we start including interactive theorem provers in mathematical education?
Yeah, actually, there are a lot of people trying a lot of such things. In fact, one person who has seen the audience is, of course, doing a lot of it in Cambridge, Kevin Buzzard, with the lean theorem prover. They are not yet completely ready, but they are more or less. There are a bunch of systems which are aimed for this. Should they be part of it? I think yes, certainly they should be part of it, meaning as an elective. The question is, when you first learn proofs, should you be learning them as formal proofs? I think this is, I don't know if they are quite ready, but I think they're getting close to being ready for that. How many years from now they'll be ready? Is it 2 years, 10 years? I don't know. So this will need a library. But it is true that at some level, I mean, I know my personal experiences, once I started getting familiar with formal mathematics, a lot of things that mathematicians confidently tell students about proofs, I stopped saying because I know they're not true. Okay, so in fact, you take an experiment, open a book. I did this experiment picking up Sayre's course in arithmetic because Sayre is well known to be one of the best expositors in mathematics. You just read a bunch, what is called a proof there. It is a series of claims, no actual proof in the deductions. This is true, and maybe hints as to what is true because of what is true. So we do not actually formally prove anything really in mathematics. So since then, I've started saying that you have to be precise enough that we know that you can't prove false statements just as easily as true statements. Okay, so that would be a correct proof. A correct proof should at least bring out why this is true when a statement that is equally related to what you say, which is false, doesn't follow. So yeah, so in that sense, I think there is a bit of a necessity in as soon as you have the opportunity. Now, I don't know if yeah, you can look around and see. Now, in terms of as a side thing,
So I guess
worth learning by yourself, certainly.
Siddharth, there is a related question. Maybe you can
sure.
answer it at the same time. What can you suggest to young mathematical students?
What can I suggest to young mathematical students? I very strongly hesitate to suggest to them. Well, one thing I would suggest, go and look at some formal proofs. So I'm optimistic. I have a venture which will probably fail. I'll be the only one paying the price for failure, and it's not much of a price. So I will hesitate to encourage this. But I will certainly, one thing I will encourage. One is read up about this area, learn. But certainly the formal proof systems, things like lean theorem prover, are actually doing a lot of great stuff. And this is not, this is going to happen. It's not things that we hope will happen, or they're happening. They're happening even as we speak. And so while you use your time well, I think to go and look at these, they're also very welcoming and friendly communities. There are other sites. There is this language called Idris, which is aimed at system programming, which is a different way, which I find very fascinating because it is it's a type checker which so lean theorem prover is only a theorem prover. This is a programming language which is meant to actually run, but which also can incorporate theorems in it. So there are many systems that are experimental. Idris, I'll mention lean prover. Coq I'm less familiar with, but it actually has a larger library, so I'm not going to comment about the difference between these two. There's I don't know, but certainly I think getting the formal proving is certainly something which you can enjoy and contribute to. And if you are young today, you say you're going to be probably active scientist 20 years from now, by which time these things would have gone very far. So certainly it's worth, yeah.
Yeah. Okay. So I think maybe with that, let's I guess on behalf of everybody who attended, I guess I would express my thanks to you for giving this great talk. And I have just posted that the slides will be on the web. So some of the requests were about the slides. So the slides will be put up on the web, and the YouTube recording of this session will also be on YouTube in some short amount of time. I mean, right now it's live. Eventually, it will become available also. So thanks, Siddharth.
Okay, thanks a lot. Thank you, everyone who was present. And thanks, ICTS and Amit Gadgil.
Yeah. Okay, bye.